Greetings to all. Myself Dr.A.Mydeen Bibi from Department of Mathematics, the Standard Fireworks Rajaratnam College for Women. My session is about linear algebra, that is important concept, that linear independence and linear dependence. First of all, we are going to see about the learning objectives of this session. The first one is understanding the concepts of linear independence and linear dependence. The next one is test given the set of vectors are linearly independent or linearly dependent. The next one is some characterizations, some important characterizations of linear independence and linear dependence. First, we want to know about some of the definitions that is important to this concept, that is we are going to find the linear independence. So first one is I am going to see about the linear span. First we need to know about the linear span. The set of all linear combinations of finite sets of elements of S is called the linear span of S and is denoted by L of S. Because we are using the linear span in finite dimensional, we are using the finite dimensional definition in linear independence. If S is a subset of V3 of R which spans the whole space V3 of R, then L of S is equal to V3 of R. So like this, we need to find the whole space span in all the vector spaces, that is Vn of R, complex space and all these things. Right. Next, I am going to see the important definition, that finite dimensional. If the vector space V is said to be finite dimensional, if there exists a subset of V such that L of S is equal to V. If S is a subset of V3 of R which spans the whole space V3 of R, then the linear span is L of S is equal to V3 of R. If the vector space V is said to be finite dimensional, if there exists a finite subset of V such that L of S is equal to the vector space V. Some examples for the finite dimensional is given here, that is V3 of R, Vn of R, also the C. Which one is the subset I am giving that? Linear span of that subset is spans the whole space is called the finite dimensional. Right. Next we are going for the important definition, that is linear independence and linear dependence. Just I am giving the definition for this linear independence and linear dependence, but there is more concepts regarding in linear independence and linear dependence. That linear independence is the central concept in linear algebra. If the vectors are linearly independent, then there exists a linear combination of scalar and vectors, and all the scalars must be 0. If they are not linearly independent, then they are linearly independent. A vector space can be of finite dimension or infinite dimension on the maximum number of linear independent vectors. A sequence of vectors contains the same vector twice, it is necessarily dependent. A sequence of vectors is linearly independent if and only if 0 can be represented as the linear combination of its vectors in a unique way. So finding linear independence. Some of the set of vectors are given. We are going to find the linear independence regarding that vectors. So we need to write the linear combination for the vectors given. So I am giving the linear combinations with the scalars, that is alpha 1 with the vector plus alpha 2 with the vector and alpha 3 with the vector. We are going to find that whether it is linear independence or dependence. So we are having a linear combination and we are going to solve the equation, right. So when we solve the equation, all the scalars are 0, then the given vectors are linearly independent, otherwise it is linearly dependent, right. So when we are finding the linear independence, we need to find that one subset is given. If it is containing the 0 vector, then the given vectors are linearly dependent definitely. So when we are finding, for example, I am taking S is equal to 0, V1, V2 and so on Vn. Clearly I am having a linear combination for that 0 vectors where alpha is any element of the field F. Hence for any alpha not equal to 0, we get a non-trivial linear combination of vectors in S giving the 0 vector, hence S is linearly dependent. Finding linear dependence. So we know about the linear independence, whether the linear combination of all the set of scalars are 0, then it is linearly independent. Whether the scalars are not 0, then the given vectors are linearly dependent. So I am giving one simple example for this. In V3 of R, I am taking some vectors. I am going to prove whether it is linearly independent or linearly dependent. I am having a linear combination in that vectors, given vectors. when we solve the equations, whether all the scalars are 0 or not 0. If it is not 0, then the given vectors are linearly dependent. Some characterizations of linear independence and dependence. Why we are giving some characterizations? It is easily to find that whether given vectors are linearly independent or dependent. If in finding linear independence, we have some properties to find easily whether it is linearly independent or dependent. One of them is a subset S of V. I am having any subset of a linearly independent set is linearly independent. So I am taking one subset. For let V be a vector space. I am taking S be a subset of that vector space. I am taking another subset that containing S, that is S dash. I am taking S dash is a subset of S without loss of generality. What is meant by without loss of generality? So we should not change any hypothesis given in that, right. So we take S is equal to V1, V2 and so on, Vn, Vk be the set of vectors. That is, I am having n vectors. In the n vectors, I am taking the least positive integer k, such that suppose S dash is linearly dependent set. If it is a dependent set, all the scalars, not all the scalars are 0, right. So such that I am having a linear combination for that. If the linear combination is not 0, it is a trivial non-linear combination giving the 0 vectors. Hence S is linearly dependent set, which is a contradiction because S is a linearly independent set. So any subset of a linear independent set is linearly independent. Likewise, any subset of a linearly independent set is linearly independent. Likewise, any set containing a linearly dependent set is also a linearly dependent set. Let V be a vector space and S be a linearly dependent set. I am taking one more subset of S that is containing in S, that is S dash. Let S dash containing in S, so S dash is linearly independent. If I am taking, if S is linearly independent set, then S is also a linearly independent set. Since any subset of a linearly independent set is linearly independent, now only we see the characterization of that. So S is linearly independent, which contain the subset S dash is also linearly independent. That there is a contradiction regarding that, hence S dash is linearly dependent, right. One more characterizations I am having, that is S is equal to V1, V2 and so on, Vn be a linearly independent set of vectors in a field of, in a vector space over a field F, right. Then every element of L of S can be uniquely written in the form alpha 1 V1 plus alpha 2 V2 plus and so on alpha n Vn. What I am saying, every element of the linear span can be written uniquely in the form of the linear combination. So we need to prove the uniqueness regarding this. So I am taking two more linear combinations with the scalars alpha and scalars beta. So I am having two linear combinations in that. So when we are having that linear combinations alpha 1 minus beta 1, alpha 2 minus beta 2 and so on alpha n minus beta n. Here we are having, since S is linearly independent, for all that all the scalars are 0, therefore alpha I minus beta I is also 0. So alpha I equal to beta I, the uniqueness proved here. Let S is equal to V1, V2 and so on Vn be a linearly independent set of vectors V if and only if there exists a vectors in S such that Vk is a linear combination of the preceding vectors of the n vectors, given n vectors. So I am taking that some subset S is equal to V1, V2 and so on Vn. There is a linearly independent set of vectors. I am having a linear combination for n vectors. In between there exists a least positive integer k such that Vk, I am taking Vk. So alpha 1 V1 plus alpha 2 V2 plus and so on alpha k Vk. Some of the vectors given in least positive integer before the n positive integers. So I am going to prove that Vk is a linear combination of the preceding vectors V1, V2 and so on Vk minus 1. So how we will prove this? So we are having a linear combination on that. I am going to take that all the vectors are 0 regarding if it is linearly independent. But it is, suppose I am taking all the vectors are linearly dependent, so all the vectors not to be 0. So some of the vectors, not all the scalars are 0. So some of the scalars must be some non-negative elements. So Vk is a preceding, Vk is a linear combination of the preceding vectors when it is linearly dependent. Okay. So we proved that some of the vectors, I am taking some S is equal to V1, V2 and so on n vectors. Just now we know the characterization that there is a positive integer Vk, that is Vk is a linear combination of the preceding vectors. We need to prove with the example for this. If I am taking in V3 of R, vector space V3 of R, I am taking 3 vectors. In that vectors, I am taking one more vector 1, 1, 1. We can say that 1, 1, 1 is a linear combination of the preceding vectors. So easily we can prove that 1, 1, 1 is a linear combination of the preceding vectors that given in the V3 of R. Hence S is linearly dependent set. If any one vector can be expressed as a linear combination of the preceding vectors, then definitely the subset is linearly dependent set. Yes, I am going for the brief explanation about linear span of the subset S and S dash. So let V be a vector space over E. Let S is equal to V1, V2 and so on. Let S is equal to V1, V2 and so on Vn. Then the linear span of S is equal to W I am taking. There exists a subset, linearly independent subset S dash of S such that the linear span of S dash is also equal to W because S dash containing in S. So we know some of the characterization regarding the subsets, that is if S is linearly independent, then S dash should be linearly independent. If S is linearly dependent, then S should be any subset of a linearly independent set is linearly independent. Also any subset of a linearly dependent set must be linearly dependent. Likewise, I am taking S dash, S1, S2, obtaining like this we are having lot of subsets for the regarding positive integers. When we have a linear combination on that, if it is linearly independent, definitely all the scalars must be 0. If it is linearly dependent, definitely any one of the scalars must be not all 0. So if not, we are continuing the above process of removing all the vectors from S1 like this, which is a linear combination of the preceding vectors. Using that characterization, we can prove that we can arrive a linear independent subset S dash of S such that L of S dash is also equal to W. I hope you all get the detailed explanations about linear independence and linear dependence. Some of the characterizations also we recall here. So some of the problems we proved here. I definitely hope that you all get lot of information regarding linear independence and linear dependence. Thank you so much.